in square brackets with a type before it. Oh, so that's our first lesson in flat assembly. So if I say word seed, let's see if that solves the problem. If we get past that line now. We do. Okay, so now we can fix all of our variables. So now we just look for, here's menu, which I assume menu is also. Menu is a, oh, that's weird, it got past menu. The menu is a pointer to this string, which we're going to have to rework, because if we're going to write our own write routines, we're going to not use $ termination. That's kind of gross. So here's the die. We have a lot of those die W's. Let's replace them. There we go. So now we have the word die. Then we have CW here, so we could actually just do the same thing with CW everywhere. CW. Seed. Replace all. Okay. The reason that I picked this program is if we come over here real quick and just check out this com file. So if we ls a6 dice.com, you can see it was 304 bytes only, and we have 512, and this is for the entire program. So if we do dump it, you can see like a lot of this string, this one string here that prints that menu at the top of the screen, and then a $, is a new line, and $, is like a quarter of the file. So we should have no problem getting this in there. And in fact, I don't think there's, what's in the file after, what's in the assembler after that? Oh, you know what, that might be, that's probably the write routine. It's probably the write routine. So this is probably where the program starts, because this is there's a DOS.com file. So, you know, people live in the modern world where we use exe files, but back when I was tiny and into when I was first learning DOS, the com file was an extension. It was really designed for running 16-bit machine programs that didn't get too big. So a lot of the early DOS tools were .com files. Command com was obviously a com file, and whereas an exe file has actually sections in it with a header that says how to lay it out and what's code and what's data, and you have your text sections and stuff. Here, what you have is literally, it's just going to load it. When it loads it, it puts what's the first byte of the file at address 100 in memory, and then it just runs this instruction, right? And if we check, like, here's the 1A for that int1A instruction, like, you can really see that it's literally just, it starts right up doing matter of fact, you can see all the CDs, right? So CD, here's CD21, which was the next one. Oh, here's a CD10. CD16. So those CD must be the int instruction. And then there they all are. And so it would really just start there and start running. And so it was very, very easy to write these. I mean, you could even hand assemble them if you had a assembly reference, and it wasn't that painful for early assembly. And obviously, A86 was a assembler at the time. It was a shareware assembler that I used to write this program. And so you literally could just put things wherever, and you could make these really tight assembly programs, which, at the time it was kind of fun to see how small of a program you could write. And, for a modern executable, 304. I mean, I was saying how easy it would be to write this program in C, but if you could write it in C and get it down to 304 bytes, that would be pretty slick. Maybe I'll try that at some point. But for now, being that we have 512 bytes that we can put in the boot sector, and this guy's 304 bytes, we should be able to make that work. Now, we are going to have to get a little bit of a increase because we're going to have to implement these DOS functions. But if we're careful about it, we should be okay. So let's continue. So starting at the top, so let's actually clean this file up a little bit. Put a little header up here. I actually like this format. Then this is just like, I don't know, simple dice roller program written for A86, ported to, that doesn't matter. I'm just going to say simple dice roller program. I will actually put a subtext of can run from master boot record. And that's obviously not true yet, but we'll capitalize master boot record. Written for FASM. Ported from 86. There we go. Okay, so now we have some notes here that when I look at this 2 decades from now, I can have some idea what it means. Okay, so this first routine, as I went through before, we set the high. This just sets this seed value off of the random number. Sets the seed value that we're going to use for random number generation off of the fastest changing part of the BIOS clock. That's very straightforward. Then this next one clears the screen. So let's double check that that's not a. So we check in 10. It was in 10. So we're setting AX to 3. So that's AH0, AL03. So AH0, AL. So apparently the way this is clearing the screen is by setting the video mode. Which is probably fine. We'll probably get better descriptions of some of this stuff. But 03, let's see if we can do. I'll Google it. Int 10H. Huh. So int 10H, that's Wikipedia. Set video mode. So I set it to 80 by 25 mode. This isn't going to work on MDA adapters, but that's okay. I don't think that's going to come up. And here's the big thing in the notes right here. When the mode is changed, the screen is cleared. So this guy is clearing the screen the not recommended way. But only because they say, oh, it's going to take a little longer. So and we're not doing anything here though that's super time critical. We're not displaying frames in a graphical context, so because it's literally going to be back and forth text UI. So we'll leave that, and we can visit that later though. This is why I do these things, to learn. So now we have menu, which is that one, which we do want to move this actual address into this. So probably by, okay, I see. So when you do this, this is, it's indirect versus direct addressing mode. So here this is going to move X into the location of seed, whereas this puts literally the value of the address of where that menu starts into DX. And then it comes down, and then it moves 9 into AH and calls int 21. So this is going to be our first big print a string problem. So if we just to review that though, make sure it's not. So that was 9. Output character string. So if you put into DSDX the segment offset of the string. Now DS we don't have to set because in COM files our segments all default to pointing to the same segment because they assumed you were basically operating in a 16-bit chunk of memory. That might not be true in the long run, but for now, we'll keep that the way it was. And this was, the string has to be terminated with a $. So that's fine. We're going to actually change this, right? So we're going to call, we could actually just go in here and just call our new routine and say, we're going to make a routine called writeString that does the right thing. But I kind of want to get to the point where this thing assembles successfully first. And then once we have that, then we can go back and start adding the additional methods we need. Read in a character. So this guy looks to be int 16, AH0. So we're going to look this one up, make sure that it makes sense as well. When I was first doing this, I didn't have regular access to the internet like we do now, and Google wasn't an option. Well, I had just a document with a handful of the interrupts described in them. Now, it was fortunately an electrical file. So this guy reads from the keyboard, and you can get either an ASCII character code or a scan code. Well, you actually get both, but you could use either. So if you look in my program, we use AL, which is the ASCII character code. So we take that ASCII code for what we read, and then we compare it to 31H. Now, this is a mess, because these should all be like character constants rather than the numbers for them. 30 hex is where 0 is in the ASCII table. I should probably, let's bring up an ASCII table here just so people can see it. Images. Go to this Wikipedia article, is probably going to be great. Okay, so we're using the hex column here, right? And so you see 30 is 0. So if you want to give a number, it's just 3 and that number in hex. So this checks for, did you push 1 or 2 or 3? And this is a non-blocking character read. Sorry, this is a blocking character read, but it reads a single character. It's not blocking until you hit like enter, right? Like in C, if you just do like a scanf or a cin read, it's buffered, so it will not. It's gonna wait till you hit enter. It's always looking for those new lines. Whereas this, it's literally as soon as you hit one key, it returns that key. So then this is basically like a giant switch case statement where we check to see if they hit the numbers 1 through 7. And if they hit 1 through 7, right, 1 through 7 is mapping to a die. So we move the correct number into the die we want to use. And it looks like this is probably using an immediate value move. So there's no registers involved here at all. And so you can see that we compare and then jump if it isn't the value you want to the next comparison. Now there's actually a much more efficient way to do this, right? We could have done this with a jump table by like subtracting 31 out of it, and if it's less than 7, no wait, 31, so if it's less than 7, then we grab a value, and if it's greater than 7, we then look at what the next thing is. That's an optimization that maybe we'll even factor in there. Okay, then here, 71. So, I see. They're literally named. The symbol says, so this is checking if it was a 2, if it was a 4, if it was a 5, 6, 7, Q, and T. And so those are all the commands that we can filter on this thing. And if we go back to our ASCII table, right, so it's Q is 71 and T is 74. 71, sorry, is a Q, and 74 is a T. Now, this is requiring you to hit the lowercase version. So that means if you hit Shift or have caps lock on, it's not going to work. We could actually use the scan code, though, to get around that issue, because the scan code's tied to the actual key that's pressed. But then the numpad numbers won't work, because the numpad numbers will return this. But what we could do is we could check for uppercase or lowercase. Another optimization, maybe. In the future, I think we're going to go for trying to get this to work as it was. So check C. Interestingly, this guy goes... So this guy then checks for if it's the C character. And then if that's not, then it goes to continue. Which makes me wonder, you know what, I didn't try hitting a invalid key in here. Oh, I know what's going to happen. Dice starts quite large. You're going to come down here. If it's not C, we go to continue, which is going to roll the die. This is all just dice rolling logic. We'll go through this in a moment. But so that means if you hit just random junk. Hey, is this guy going to run through? Yeah, this is not the best way to write a piece of code. Because it literally is going to do all these comparisons and then eventually fall through. So this isn't really a switch case even. It's like a weird... It's basically a nested run of ifs. Young Ted gets a C, I guess, on this. It's not great. I'm probably grading him too generously. But, I mean, it works, I guess. But so when you come down here, you're going to get a value. And so it's going to run if you hit the wrong key, regardless. Actually, let's test that. So fortunately, I have the original stone box. So if we hit, let's just hit a random character like U. Yeah, so it gives us a random number between probably 0 and 64,000, right? Because it's a 16-bit number. Oh, you know, that might have been intentional. Because once you said it once, though, so I just hit 2 to get it to roll a die 6. But now if I hit space or something, it's going to roll. If I hit anything else now, it's going to roll just that die 6. Like if I hit 9, 0. And if I clear it, And that still remains. Interesting. So I must have added clear later because of the way the code's written, right? Like forensic archaeology here or something. So this part basically gets a random number, and then this part, you know, you're applying the die to it as a limitation, and then you increment the total, which is another one that we need to turn to Word, and then we write that value out. Then it jumps back to label A, which is all the way back up here at the top, where we wait to read the next character. So yeah, I'm gonna go more into why this does it the way it does it. It's basically a very simple, like multiply based random number generator. It's not great. We could probably replace this with something slightly better. Maybe put a couple extra instructions into our random number generator for our dice program. But first, let's fix total. So we're going to come down here. Total. Total. Replace all. Okay. So I think we are now to the point where this will probably build. Well, or assemble. Let's see what happens. So we save it. Oh, probably had a total that missed the. Yep. That should have been. Probably the explicitly calling it a word total was probably not necessary in the A86, so probably missed one. All that time ago. Undefined symbol right. So now it's getting to the point where that function right doesn't exist. So what we're going to do is we'll add the right function. So it put the right function at the end in the old one, so we'll put it down here too. A little more. We're going to go lowercase. So we're going to call it right. And we're going to call it actually right string. Go a little more modern on it there. And then we're going to give it, and all we're going to do is have this return. So it's not going to be best, but it's gonna get the job done. There's literally nothing that a function has to do other than return. So we're not going to modify any of the registers. We're just going to come in, come out. This program isn't really expecting right to do anything. So, oh, this isn't actually right string. This is right num, right? There's just two calls to it, so let's change those to right num and right num. So let's give it a run. Okay, so it's successfully assembled. That is a big win. Next time, we will look at some of the memory differences between a COM file and a boot sector, and construct a makefile to help with the build, test, and debug cycle. Subscribe or come back often to catch that. Or come follow me on GitHub. Good luck, and keep on crafting.